All right, welcome back. We're now on section 4, which I like to call the change gas laws. All right, so what do I mean by that? So let's revisit. Remember that gases and their physical state can be described with the following 4 parameters. So gases and their behavior can change with pressure, volume, temperature, and then just simply the quantity of gases, which is the number of moles. So any of those 4 variables, if they're changed, can affect the nature of a gas and how it behaves. So the change gas laws that we're about to look at essentially looks at the initial conditions and then the final conditions if one of the variables was changed. And so let's talk about that a little bit. So in the last section we just went through, we talked about the ideal gas law, right? And the ideal gas law was Pivner. Okay, so Pivner, PV equals nRT. Now, if I were to rewrite this equation in terms of R, you would end up getting this, right? So R, which remember is the gas constant, is really just pressure and volume divided by the product of number of moles and temperature. Now remember, R is a gas constant, okay? So that means that R always has to be the same value. So what that means is no matter what the conditions are for pressure, volume, moles, and temperature, when you calculate this, it always has to equal the gas constant. So let's take a look at a gas that was under initial conditions of pressure, volume, number of moles, and temperature. So the I's stand for initial, okay, whatever they are. Now let's suppose we change those conditions. Let's say we change the pressure, the volume, the number of moles, and the temperature. So the F's stand for final. Well, no matter what the initial conditions are and what the final conditions are, we know that the calculation of those 4 variables always has to equal R. So we could actually take this, and we can set them equal to each other since we know they both equal R. And so you end up getting this this equality, if you will. Pi times Vi over Ni times Ti will equal Pf times Vf over Nf times Tf. Now that's a lot, right? That's a lot of things. But what you're going to see is that all the gas laws that we look at in this section come from this equality. And what we do is we just remove any variables that may not apply. Just FYI, just so you know, this equality right here is oftentimes referred to as the combined gas law. And the reason for that, obviously based on the name, is we're combining everything into one succinct equation, one succinct equality. So as we go forward, what I tell students is when they are looking at memorizing gas laws, don't think to memorize gas laws. If you can just remember this, and then remove everything that you don't need, then you'll have the equation that you need to use to solve the problem. All of this will make sense when we start going through the gas law, so just keep that in mind. Okay, so here's a Cliff's Notes slide for you. All the gas laws we're going to learn come from, are listed right here. So we're going to go through 4. We're going to go through Boyles Law, Charles Law, Guy-Lussac's Law, and then Avogadro's Law. Real quickly, we'll go through each one more specifically, but just real quickly, Boyles Law is only going to look at pressure and volume. Charles' Law only looks at the relationship between volume and temperature. Guy-Lussac's Law looks at pressure and temperature only. And then Avogadro's Law looks at volume and number of moles. And we got the formulas here, okay, and I'm going to go over those on the subsequent slides we go through, as well as it talks about the relationship between the variables. Now, just real quickly, to demonstrate what I was talking about on the previous slide, take, for example, Boyles' Law, right? So Boyles' Law, notice it only looks at how pressure and volume relate to each other. It doesn't mention moles, it doesn't mention temperature. So since it doesn't look at those, it assumes that they're constant. So if I were to look at this combined gas law up here and just get rid of number of moles and temperature, notice what you're left with. You're left with this simplified version, which is just pressure times volume equals pressure times volume. And that's exactly what you've got right there. So that's what I was saying before. Don't worry about, oh my God, I have to memorize this one and this one and this one and this one. I have to memorize all these equations. just memorize the 1 and then just get rid of the variables that aren't necessary. Like, for example, in Charles' law, it only looks at volume and temperature. So if I were to look at volume and temperature only, meaning get rid of pressure, get rid of moles, look at what you're left with. V over T equals V over T. And that's what you have right here. So that's what I was saying before. Before we move on, I just wanted to read this down here. Notice how the combined gas law is a combination of all of that. So this right here is just talking about what I just mentioned, where as long as you know the combined gas law's equation, you can figure out all these other equations down here. So without further ado, let's get into it. Okay, so the first law we're going to talk about is Boyles Law. And Boyles Law, like I said, looks at the relationship between pressure and volume only. So it assumes that the number of moles and your temperature remain constant. They're not changing. So the equation that we're left with when we just look at pressure and volume is P1 times V1 equals P2 times V2. Notice sometimes we use numbers instead of letters. So instead of P initial equals and P final, we say P1 and P2. So now I want you to think about this. So let me write this down here so I have a little space. Let's assume your initial pressure was 1 atmosphere and your initial volume was 10 liters. Okay, so what's the product of that? 1 times 10. Well, it's 10, right? So what then if the atmospheres or pressure changed to 2, what then would have to be the volume in order for it to still equal 10, right? Because they both need to always equal 10. And it would be 5 liters, right? It'd have to be 5 because 2 times 5 is 10. So notice what happened to the pressure between these two. The pressure increased, right? Because we went from 1 to 2. What happened to the volume as we went between these two? The volume ended up decreasing. Do you see that? It went from 10 liters to 5 liters. And so we call that an inverse relationship. As pressure increases, volume decreases. That's the relationship between pressure and volume. Okay? And if you play around with the numbers, you can see that. So that's a good thing to remember. So not only remember Boyles' law's equation, but also remember the relationship. Okay? Now, since you have pressure on both sides of the equal sign, as well as volume, it does not matter what units they're in. So remember ideal gas law, we had very specific units for pressure and for volume. Pressure could be in any units. It could be in millimeters of mercury, it could be in torr, as long as you have the same unit on both sides. Same thing with volume. Volume doesn't have to be in liters. It could be in milliliters. Just know that it would then be milliliters on the right side. So keep that in mind. All right, so let's take a look at an example. I already have the work filled out here for you, but we can take a look as far as just the setup. So example 7, what will be the pressure of 21 milliliters of a gas if its pressure was 731 millimeters of mercury at 43 milliliters? So essentially it's saying, okay, well, when the gas had a volume of 43 milliliters, its pressure was 731. What would be the new pressure, so P2, if we reduced the volume down to 21 milliliters? So you can see you've got your P1 and your V1 here. You're solving for P2 knowing that your V2 is 21 milliliters. Now, real quickly, before we do any calculations, which, like I said, the math is right there, notice the volume. What happens to the volume? The volume decreases. So we would expect the pressure to increase. And we can see that it does. The original pressure was 731, and the final pressure was about 1,500. Notice we rounded to 1,500 millimeters of mercury because of sig figs. There's 2 sig figs with these volumes, so we round it to 1,500. But also notice we didn't have to convert milliliters, right? And we didn't have to convert millimeters of mercury, so long as we know that our final answer will be in millimeters of mercury. All right, let's look at our next law, Charles' law. So Charles' law is looking at volume and temperature, so it's assuming pressure and number of moles is going to remain constant. Okay, and so if you think about, let's say our original volume was 10 liters, and our original temperature is 1 Kelvin. I'm just making up numbers here. Notice that the temperature has to be in Kelvin. If our, so 10 divided by 1, what is that? It's 10. So that means this side also has to equal 10 because they're equal to each other. So what if the volume changed to 20 liters? What would have to be the new temperature so that it still equaled 10? Well, 20 divided by what would give you 10? And that would be 2 Kelvin. So what happened with the volume here? The volume increased. It went from 10 to 20. What happened to the temperature? It also increased. It went from 1 to 2. So both volume and temperature increase in the same direction. That's known as a direct relationship. Okay? Now remember, I said this earlier in one of the videos that when you're looking at a gas law with temperature, it has to be in Kelvin. That's very important. So make sure that if it's in Celsius, you need to convert by adding 273.15, which hopefully by now you are familiar with. So let's look at an example. Example number 8. If a 1.50 liter balloon expands to 3.00 liters, what would be the new temperature if the original temperature was 25.0 degrees Celsius? Okay, so I could write out V1 equals 1.50 liters. Its new volume, so V2, expands to 3.00 liters. The original temperature was 25.0 degrees Celsius. What then is the final temperature? Okay, so let's set this problem up, right? So when I write all of this information out, it becomes clear to me that I'm looking at Charles' law. So Charles' law is V1 over T1 equals V2 over T2. Okay, now some of you may have noticed that, oh, look what happens between volume 1 and volume 2. It doubles. It exactly doubles. Do you see that? So some of you may be thinking, okay, well, if the volume doubles, then temperature must also double, since it's a direct relationship. And you're absolutely right. If volume doubles, so does temperature. But be careful, it's not the temperature in Celsius that doubles, it's the temperature in Kelvin that doubles. So it would be incorrect to say, oh, the original temperature was 25 degrees Celsius, the new temperature must be 50 degrees Celsius. That is incorrect. Instead, you have to do it in Kelvin. So let's actually work the problem out so you can see what I'm talking about. So we have our setup right here, and I'm going to do it in a different color. All right, so I'm just going to plug it in exactly how we've got over here. So V1 is 1.50 liters. T1 is 25 Celsius, but we need to convert 25 Celsius into Kelvin. Okay, so I'm going to add the 273.15 to that. And when I do that, I end up getting 298.2 Kelvin. Let me write that a little bit clearer. Sorry about that. There we go. Okay, and that's equal to our new volume. V2 expands to 3.00 liters. So the question then is, what is T2? All right. At this point, this is algebra, so however you decide to solve for T2 is up to you. What I tell students that may not be familiar with the algebra or comfortable is I tell them to cross multiply. Okay, so you're going to, because of the equality, you can do this. And so it would look like 1.50 liters times T2, since that's what's there, is equal to the 298.2 Kelvin times 3.00 liters. So that's this cross multiplying. And so we're going to solve for T2 by dividing both sides by 1.50 liters. Okay, so let me get our calculator out, see what I end up getting. All right, I end up getting, and I'm going to go back to blue here, or pink here, excuse me, so it shows up. So I end up getting that my new temperature, my final temperature, would be 596.4 Kelvin. And you can see the Kelvin ends up doubling. It's not the Celsius that ends up doubling, it's the Kelvin. Now, since our original temperature was in Celsius, even though the problem did not ask for it, you should report the final answer in Celsius. So I'm going to convert this Kelvin back to Celsius by subtracting 273.15. And I end up getting that my new temperature in Celsius is approximately 323.3 degrees Celsius. You can see that it's not the Celsius that doubles, it's the Kelvin that doubles. So keep that in mind. All right, we're going to continue with the change gas laws in the next video.